Pop quiz. You connect a battery with a positive terminal on the P side and the negative terminal on the N side of a silicon PN junction. What happens next? A. The barrier gets taller and current drops. B. The barrier gets lower and current rises. C. Nothing changes because the two currents still cancel. Hold your answer. Time's up. The correct answer is B. The barrier gets lower and current rises. But to really understand why that happens, we first need to recall what the junction looks like before any battery is connected. Before we connect any battery, a PN junction at equilibrium has two currents. Diffusion current comes from majority carriers trying to spread out, and drift current comes from minority carriers pulled by the electric field in the depletion region. At equilibrium, they are equal and opposite, so total current is zero. Now that we know what zero current really means at equilibrium, we're ready to see what changes when we attach a battery and start increasing the voltage. In this video, forward bias in a PN junction, we will see what happens when we attach a battery and slowly increase the voltage, and why the current shoots up in a very nonlinear way. Let's set up the circuit clearly. First, we connect the positive terminal to the P-type side and the negative terminal to the N-type side. With zero applied voltage, the ammeter reads zero because diffusion and drift still cancel. To understand why current rises once we apply voltage, remember what the depletion region represents. At equilibrium, the depletion region acts like a potential barrier. For silicon at room temperature, you can think of that barrier as roughly 0.7 volts. Now, let's begin increasing the applied voltage. We apply a small forward voltage, like 0.2 volts. An easy way to picture this is that the battery lowers the barrier, making it easier for majority carriers to cross. So diffusion current increases. Drift current changes only a tiny amount because minority carriers are scarce, so drift stays roughly the same. That means the currents no longer cancel, and we get a net current. And because current in a series circuit is the same everywhere, the current inside the diode from P to N matches the current through the external wires. The ammeter now shows a non-zero reading. What happens if we increase the voltage even more? Let us turn the voltage up more, say to about 0.4 volts. The barrier lowers further, the depletion region narrows further, and diffusion increases again. But here's the key. If you double the voltage, the diffusion current does not simply double, it increases by much more. This response is strongly nonlinear. A helpful analogy can make this clearer. Think of it like a gate that is barely cracked open at first, then suddenly swings wide. A small change in forward voltage can cause a much larger change in how many carriers cross the junction. As you approach about 0.7 volts for silicon, the barrier is almost gone. The depletion region nearly vanishes, and majority carriers can cross much more freely. Diffusion current skyrockets, and the circuit current becomes very large compared with a tiny current at low voltage. This specific battery connection has a name. Connecting positive to P-type and negative to N-type is called forward bias. In forward bias, a PN junction conducts heavily once the applied voltage is high enough to significantly lower the barrier. It is important to clear up a common misconception here. Some students think both diffusion and drift rise together in forward bias. In reality, the big change is diffusion. Drift is still limited by the small number of minority carriers, so it stays roughly constant compared with the huge growth in diffusion. So far, we have covered that forward bias lowers the junction barrier and increases diffusion current, which creates a net current from P to N through the diode and through the entire circuit. Ready to lock it in? Tap the link for study guides and flashcards on this topic, so you can keep learning without missing a beat. Now let's connect this physical picture to the graph you usually see. On a diode current voltage graph, as you slowly increase the forward voltage, current stays tiny at first, then rises sharply as the barrier becomes easier to cross. Now, here is a useful comparison. Different materials have different effective barrier sizes. A silicon diode typically needs a higher forward voltage than a germanium diode to conduct strongly. The core story is the same, but the steep rise happens at a different point. Another common error is mixing up the battery connection. If you reverse the battery, the barrier grows taller and the depletion region widens. Diffusion becomes even harder, so current is nearly zero except for a tiny minority carrier drift. That is reverse bias, the opposite behavior of what we are focusing on today. So here is a simple step-by-step method you can use on any problem. First, check polarity. Positive to P and negative to N means forward bias. Second, forward bias lowers the barrier in the depletion region. Third, lowering the barrier boosts majority carrier diffusion, so diffusion dominates and total current increases rapidly with voltage. If you remember just one visual, remember these snapshots. A small forward voltage gives a small current. A bit more voltage gives a much larger current. Near the typical silicon forward value, current can become very large. Let's close the loop and recap. At equilibrium, diffusion and drift currents cancel. Forward bias lowers the barrier and narrows the depletion region. Diffusion rises non-linearly and dominates, so net current flows from P to N, and the diode conducts strongly. Ready to quiz yourself with the content covered in this video? Check out the link in the description, where you'll find Quizlet content made just for you.